Class, this video is on angles of elevation and depression. Now, before we start getting any further, really and truly, the simplest way to put it is angles of elevation and depression is a way for us to solve problems, geometric problems, using sine, cosine, and tangent in a word problem form. Instead of just spouting out and getting a bunch of problems with triangles and solving this and this, angles of elevation and depression is a lot of ways to apply trigonometric ratios and trigonometric problems into a real world application. And so since we do that, we have special names for angles of elevation, angles of elevation and angles of depression. Now the angle of elevation, if we're looking at our particular picture here, we have an observer down on the floor or down on the ground looking up at a person or a balloon, a hot air balloon, and we can see that an angle, as we're looking, the angle of elevation of an object as seen by an observer is the angle between the horizontal and the line from the object to the observer eyes, which is the line of sight. If we are looking at this particular one, we have the horizontal here, and the line of sight is up to the hot air balloon. So with the horizon here up to here, we have that angle of elevation. Now with the angle of elevation drawn or seen, we see that it's 38 degrees. Also, if the object is below the level of the observer, so if we were up here in the balloon and we were looking down from the horizon, then our angle of line of sight would be angle of depression. So based upon that information, as we're looking at the two horizontal line and with our line of sight, notice that in each case, what have we drawn? We have that connection between the two from the line of sight being a transversal line and with our two horizontal lines as being parallel. Notice that we have alternate interior angles. And the angle of depression is the same as the angle of elevation. So keep that in mind. It's very important that we understand that this observer's angle of depression, as they are looking down at this point, would be this observer's angle of elevation. And they are the same measure. Well, let's go through and let's look at a couple of problems for these. One here we have just a way to look at it trigonometrically and from a real life standpoint. If we're here in a boat out on the water, and as we're here on the boat and we look up and we see a plane, as we look with the horizon, notice as we look up to the plane, we create that angle of elevation. Yet if we're the pilot here, and as we look out with the horizon and look down to the boat, we create an angle of depression. And once again, these two would be the same measure. So the angle of depression would equal the angle of elevation as well. Now let's apply that particular problem. We're off in our little bitty sailboat this weekend, and we look up to the top of a lighthouse, and we see that or we are told that our line of sight, and this is our line of sight, is 200 feet. And from that horizon, as being looked down from the lighthouse, and we're being spotted, we see a 23-degree angle. Notice as we are looking here, we have a nice big right triangle with a right angle. So this is an applied property. We have an angle here, that is our theta, so we need to set this up. We're looking for x. Now recall that if we're looking for x, that is the adjacent side, so then therefore the cosine of 23 degrees would equal the adjacent over the hypotenuse. Solving the ratio, we would have 200 cosine of 23 degrees would equal our x. Now, to make sure we put that in the correct way, let's look at it. Here I have my graphing calculator, so I'm going to say 200 times cosine of 23 degrees. and enter. And we're going to round, because it is a side length, we're going to round to the nearest tenth. Therefore, x equals, oops, I forgot it, 184.1. 184.1. So if we were looking at it in this way, and we could draw this triangle back down this way, that tells us this is x as well. So the sailboat is 184 feet, 184.1 feet away from the base of the lighthouse. And that is an applied problem, the way that we can solve if we're out in the sailboat. Of course, let's look at some more examples. We are an observer in or outside, and we're looking at a tree. Common problem. Now we want to know the height of the tree. We want to know the actual combined height of the tree. We're looking for our x here. Now understand where the horizon is. The horizon goes along with our what? Our eyes. Now let's say that this is me standing here. So my eyes are 6 feet off the ground. Keep that in mind. So as an observer whose eyes is 6 feet off the ground, looks up to the top of a tree with an angle of, let's say that that angle is of 33 degrees, and the observer knows that they are standing 100 feet away from the base of the tree. We want to know how tall the tree is. Now we're not solving for x, because x, in this case, we're not solving for x right now. X is the entire height of the tree. We would have to solve for y to find the height, or the opposite side of this right triangle. And once we find the height, then we know that the height of the tree, x, would equal y plus the height of the observer's eyes. So that's the reason why we have that 6 feet here. We know that the observer's eyes are 100 feet from the base. So in relationship to our 33 degree angle, we are looking at the opposite of y and the adjacent of 100. So therefore it is the tangent. 33 degrees equals opposite over adjacent. And once again, since the value is in the denominator, we are going to multiply. So we have 100 tan 33, and that is equal to y. So we would have 100 times, we don't really have to put that, but times tangent 33. And that gives us a value of 64.9. So y equals 64.9. But that's not the height of the tree, so we'll have to add it to it. So we have 64.9 plus 6. So therefore the height of the tree is 70.9 feet. Moving on, another example. The best way we can do this is just continually working. Looking at it from a different perspective, now we know the height of the tree. And from where we're standing, we are 68 feet away. So from the base of the tree, we're sitting here and we're standing 68 feet from the tree. And we know that the height is 51 feet tall. We want to know the value of x, or let's be consistent. Instead of x, yes, let's use theta. We're looking for theta. So in relationship to our angle theta, we know that we would be using the opposite. We have to write it. Here's the opposite, here's the adjacent, here's hypotenuse. So our two values we're given are opposite and adjacent, so that is the tangent function. So tangent of theta equals 51 feet over 68 feet. Now, since we're using, or not using, but solving for an angle measure, we're going to say that theta equals the inverse tangent of 51 over 68. So in order to do that, we go shift or second, depending on your calculator, tangent. Notice that gives us that inverse of 51 divided by 68. And we want to, we can close and enter. Now, as we discussed a lot in class, if we are solving for an angle measure, we want to round that angle. Unless otherwise noted, we want to round that angle to the nearest whole number, or whole degree in this case. So notice 36.8 would round to 37 degrees. So theta equals 37 degrees. Well, let's get another one. Sorry, let's adjust and move over. Now here is one. If we're lucky enough to be a pilot, it says the angle of depressions are often used in aviation. Imagine that you are flying into an airport. Your angle of depression is 7 degrees. So as we are this pilot and we're flying in, our angle of depression is 7 degrees. And through our instruments, we know that we are 4,000 feet above the ground. How far do we have to fly before we land? Now, think about how you fly. We're not going to fly. We are flying in this direction, but we don't just fly straight across and then drop down. We are actually flying at a descent in this direction. So in this case, we would be looking for x. Now, recall that an angle of depression is the same as if we were down here at this airport trying to make our runway, would be the same as our angle of elevation. And if we have these parallel lines with the horizontal, right, then we have alternate interior angles. So therefore, this is a 7-degree angle as well. So let's clean this up and let's look at it. That means we have our right triangle here. That's horrible, but it's a right triangle. This is a 7-degree angle, and we are looking for x. So let's set up what we know. In relationship to our angle, this is our opposite side, this is our adjacent, and this is our hypotenuse. So we're given the two values of opposite and hypotenuse. So that is the sine of 7 degrees equals opposite of 4,000 divided by h, or I'm sorry, it's our hypotenuse, which is x. Now, we can solve this ratio, understand everything's over 1, but also remember that as we're solving ratios, we can, as we multiply, we can cross or we can switch. So therefore, x is equal to 4,000 divided by the sine of 7. Plugging that in our calculator, we're going to have 4,000 divided by the sine of 7 degrees. And we get an answer of 32,822 degrees. So how far is it until we land? 32,822 feet. 32,822 feet and some inches. We're going to round to the nearest whole number here. Now, if this problem happened to say how far, it says how far do you have to go before you land? Well, we don't know exactly how far that is. What if it says in miles? We can have a reference of that better. We have to convert that. Since there are 5,280 feet in a mile, we would take this amount of 32,822 and divide that by 5,280. And that would give us our distance in miles. So 32,822, 32,822 divided by 5,280 feet. That tells us that we are approximately 6.2 miles away. And we have an understanding of how far that is. So I hope that this lesson has improved your knowledge a little bit of your sine, cosine, and tangent. I just want to recall you back to the things here at the beginning, that an angle of elevation is the same as the angle of depression, depending on the orientation of where you're looking. So if we're here at the top and we're looking down, it's an angle of depression. If we're here at the bottom looking up, it's an angle of elevation. and they are always going to be the same measure.